And everybody draw what this could look like, the vector 2, 1. What could it look like? If you put a dot, you're wrong. These are not represented by a dot. Over 2 and up 1 is kind of a thing, but it's not a vector. The whole blue line, that's a vector. All right, tell me what else. Well, could a kid have actually drawn it right there? Yeah, that's still the same vector. Why? Because it goes the same, it has the same direction, and it's got the same magnitude. Okay, so if I was going to write an equation for those two, would they be different? Yeah, because they'd have different starting points. But they're the same vector. So that's weird, but true. Those are the same vector. All right, so now, would you please tell me something else we would need to know about that vector? Let's call it vector v. What's something else I need to know about vector v? Come on, this will go faster if you just pipe up, say something. All right, turn it into an equation. I like it. If we put its tail at 0, 0 right there, write an equation for this. Given it's right where I said it is, with its tail at 0, 0, what's the equation for this? Remember, this is a review day, so I'm expecting you to do it, and then I'll show you in a second if you did it right. Oscar. It starts with XY. That'll allow later conversions into parametric and even rectangular. But can you tell me what's next?
Equals 0, 0.
Keep going.
Plus lambda.
I like it.
2, 1.
Yes. Notice the vector just plopped right there. The vector goes there. This is not a point. This is a vector. That's a point. Any questions about that? Okay. What if I came up with a different vector and I called it, vector R? What would need to be the same if it was going to be parallel to this vector? What part needs to be the same? Pausing. So the vector 2, 1 needs to be the same. So if I wrote another vector down here, x, y, and I don't even care what point I start at, 5, 7. But if I have this part, 2, 1, the same, then those are what vectors? Parallel vectors. Okay, good. What if I wanted them to be perpendicular? Then you need to know the dot product of them. But wait, the dot product of them, what is that again? All right, so I'm going to actually not use this as my vector. I want to change it now. I'm going to say this is x and 4. Would you please make it, solve it, so that you can tell me what x is for these two vectors to be perpendicular? So this brings up the concept of dot product. I'm calling this vector R. This one was vector V. Dot product. Well, at least it has the word product in it. It does mean multiply, but you don't just multiply. I hope you said that 2 times x plus 1 times the 4, which is 4, had to equal 0. That's the special thing about dot products and perpendicular, is you want your dot product to equal 0. So can you just look at that and say x has to be negative what? Negative 2. X equals negative 2. Raise your hand if you had that one right. Not many people. Okay, so let's just do another more complicated vector. 1, 5, 7 and 2, 4, 6. dot product of it. What's the dot product of those two? Tadros, how do I start? Dot product, that times that. Product means multiply, right? So what's 1 times 2? Plus, I bet you can figure it out. I just did one on the board 2 seconds ago. What do you think is next? It is. That's 20. And then what do you think's next? Which is? 42. And you put it all together. 42 and 20 and 2. 64. That's the dot product. Were these two vectors here, were they parallel? No, they'd have to be exactly the same to be parallel. Let's change this 6 to an x. And then would you please tell me what x would have to be to make these perpendicular? Remember, you'd want the dot product to be 0. Lainey, how'd you start?
I did 2 plus 20 plus 7x equals 0.
And you had to all multiply and add up to 0. Good. And then this makes 22. So then I'm going to subtract 22 from both sides. And I get 7x equals negative 22. X equals negative 22/7. Raise your hand if you had that one right. Cool. Now we're on almost everybody. Do you get what dot product means? Cool. What else do you have to know? Oh, so many things. Here's a vector. We're going to call it vector v again, except it's a different vector this time. It's going to be 1, negative 2, and 3. What would it mean if I just, without saying the words, if I just said, what's that? For those that are stuck, Opal, do you remember what the words are for those? That's magnitude. Very good. Max, how do you find the magnitude?
Take the squares of each of
Yep. I thought you were going to say square root, but you're right. It's squares of them, and then you square root them. So what is the square of the 1?
1,
And what's the square of the negative 2?
4,
And the square of the 9?
9.
Sorry, dang it, square of the 3 is 9. So then, square root of?
Oh,
14, okay. So, raise your hand if you had square root of 14. Good, that's a magnitude. Okay, now, the other thing that we do with that is we say, then I want you to make this into a unit vector. But wait, you say, this is way bigger than 1. It's the square root of 14 long. So what do you do to your vector to make it be a unit vector then? Raise your hand and tell me. You know. 1 over root 14. That shrinks my answer, which would have been root 14. It shrinks that down to be equal to 1. So what? So now what if I wanted to actually be 17? You can shortcut this. I'd be fine with this on the test. You just put the 17 right there. Because you're going to multiply by 17, and that'll keep you from by accident. See what kids do sometimes? Is they remember that this kind of problem does multiply by all 3 parts. So if you do that with the 17, you might think you multiply by a 17 on the top and the bottom, and you do not. You know, when you multiply by 17, it's 17 over 1. So again, people see this and go, say I had to multiply those two. Well, 15 times 2 and 15 times 3. No, 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 no. Only the tops get multiplied. So what I'm trying to say is, when you do this problem, I'm fine with you just putting how big you want the vector right there on the top. So that being said, here's another one. Let's use vector R is 410. I'd like you to tell me what to do to this vector to make it 17 long. It's not 17 long right now. You might think it is because you got 4 squared and 1 squared, but no, no, no. It's square root of that long. So figure out how to make this first into the unit vector and then make it 17 length instead of what its current length actually is. On this one, I'd like you to check with the kid next to you. When you're done, you're going to write your answer with the 410 and something in front of it. And that'll be easy to check with your neighbor. If you do not know, then ask them to help you. Show me how you got that. I'll pause for a second. Let's go with Mr. Doge. Can you tell me what to put in front of it?
17 over root 17.
Why did you have 1 over root 17 at one point before you finished the problem?
Because that was the magnitude.
All right. And you put 1 over that to make the, what's this thing called?
Unit vector.
That's a unit vector. And then you times by 17 up here on top because you want to make it 17 times bigger. So you're right. Raise your hand if you had that one right. Cool. Yes.
Do you have to, when you multiply everything like to both sides?
You say both sides. This is not an equation. This is not like if it was 2x equals 7, you have to do things to both sides. That's not an equation. So no. All right. So now, so many things to know. What if I just, let's keep it super simple. Here's vector v again. It's the same vector. It's 1, negative 2, 3. And this is vector r again, and it's 4, 1, 0. What if I just want you to add the vectors? Can you please add those vectors? It's like you'd put them tip to tail and blah, 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 but there's a really fast way to do it. You don't have to draw them. You can if you want to. Jack B. What say you?
The vector v plus vector r equals
5, negative 1, 3, and you basically just add across the top and middle and the bottom. That's it. That's what you get when you do v plus r. Okay. Any questions about that? Okay. How about the velocity? I just introduced that one. So let's take this one, r. Can you tell me how fast it's going? Well, first I have to tell you, speed is really just how far it's going divided by how long it took. Okay, so distance equals rate times time. And the rate, if I divide by t, it's just the distance it went divided by the time it took to get there. So if I just keep it simple, and we'll assume that it's gone this much in 1 minute, hour, second, whatever, 1 unit. So let's just say it goes that far in 1 second. Okay? Then what's its speed? Well, obviously we have to know the distance, which is really the magnitude. Robbie House, what's the magnitude?
Square root of 17.
Good. So square root of 17 is the distance divided by the time. How long did it take to get there?
1 second.
1 second. And I didn't ever give you units for like how far we were going, so I'm going to say miles. Miles per second, that's going fast. But you know, when you talk in terms of like spaceships and things, they can do that. Yes?
You have to leave the 1 at the bottom.
No. But it's a rate. So what would be sad is if the kid just wrote 17. Because then all you're telling me is a magnitude. You've got to tell me a speed. So by writing it this way, at least I got the units in there. So it might not be too dumb to do that. Now, if you had said root 17 miles per second, I'd have been fine with that. All right. So that's speed. So many little things that you have to know. Let me just drop that on my desk. There's the angle formed by these two vectors. So I'm going back to the same two vectors, these two, V and R, 1, -2, 3, and 4, 1, 0. Can you tell me the angle that's formed between them? It's a formula. I'll give you about 15 seconds to recall that formula. It involves dot product. By you trying to piece that together, you are going to increase the little neural pathways of remembering this when I tell you. How many of you remembered it was V dot R? Remembered that, at least. Raise your hand if you did. Okay, good. Equals, it looks like absolute value of V, but it really means what? Magnitude of V, magnitude of R. And then what's the last thing? Yes, sir.
Cosine theta.
Yes. So, take a second and actually do this. If you don't have a calculator, then you can leave that last part off. But you will have a calculator on this next test. So you will be expected to do it with a calculator. Pausing. Okay. Who could tell me how to do the dot product? Thank you.
You multiply them and
Do. What'd you get?
final dot product.
Yep.
I got 2.
You are correct. 2 equals, and then the, looks like absolute value of V. What does that actually mean, though? Magnitude. You got it? What is it? It's a square root of, let's do it in our head quick. What's 1 squared? 1. 2 squared? 4. 3 squared? 9. 1 plus 4 plus 9. Square root of 14. And how about the square root of R? No, the absolute value of R. No. Magnitude R. Oscar.
Square root of 17.
Square root of 17. Anybody verify square root of 17 on that one? Okay, good. Then its last thing is cosine of theta. Again, I recommend you use your calculator and actually try this because that's what you'd have to do on the test tomorrow, or Friday, a couple days from now. I'm dividing by root 14, root 17 on both sides. And if you know how these works, it does save you some time because you go 2 over root 14 times 17, because you can do that, 2 roots that are multiplied. And I get that decimal, and then I find the inverse cosine of that. I'll pause for a second. We'll give that a shot. Did you guys get 0.1296 equals cosine theta, and then you do the inverse cosine of that? Anybody verify that? Okay, good. So I'm going to make sure, first, you know what I'm going to do? I'm going to make sure that my calculator is in degrees, unless I want the answer in radians, but some weird decimal radians is probably not what they're going to want. So I'm going to go into mode and make sure that I'm in degree mode. I was not. I was in radian mode. I wonder if any of you would have messed that up. Now I'm going to go inverse cosine of second answer to pull down that decimal I just had a second ago. And I get 82.55. Let's call it 82.6 degrees. Raise your hand if you had 82.6 degrees. Awesome. All right. That's the angle between two vectors. That's kind of complicated and cool that you could do that, most of you. All right. Next up, let's say that I wanted a vector equation between these 2 points. This is a point that's different than a vector. 1, 2, 3, and the point 2, 3, 4. These are points. Let's say it starts here and it goes to the other one. It matters what direction they go. Now, if you've forgotten this, it's kind of like doing that. We did this thing the other day where we had to figure out a directed line segment, and it's like that. All right, here's another way to say it. You always have to have an x and a y. Then you always have to have a point to start with, and you could start at 1, 2, 3. That's easy. Then you need like a lambda. You could have said t, you could have said anything really right there. And then the biggest mistake is people put the 2, 3, 4 right there. But remember, this is a vector right there. So you can't put 2, 3, 4. That'd be putting a point where there's supposed to be a vector. So then what's the vector? It's how much did it go up? Went up 1, up 1, up 1, 1, 1, 1. Raise your hand if you had that one right. If you didn't, then look at it close and try to figure out what I just did. Yes?
For the XY, would we catch out this as well? So a few points.
Oh, yes, good point. Thank you. We have a 3-layer one here. So it should have been X, Y, Z. Okay. Next thing I got to talk about, how could there be this many things to know? Well, that's why we have 2 review days. All right, the next one is, can you make this into little parametric equations? I'll give you a hint. The first one starts with that equals that plus that times that. That's your x equals equation. Go ahead, write out a system of parametric equations now. I would describe this test as a lot of things you have to know how to do, but none of them are super hard. So here's that first one. X equals 1 plus, now I could say lambda 1, but usually people would just say 1 lambda or just lambda. The middle equation, Robbie.
2 plus lambda 1.
Can I just say 1 lambda or just lambda?
Yeah.
Yep. All right, Amanda, the Z.
3 plus lambda.
Yes. When could that ever be handy? Well, when you have 2 of these things. Okay. Children having problems out there. I'm going to have to shut the blinds. Todd Russ, you're in charge. Can you shut the blinds, please? It's probably your friends. Okay. Anyway, back to, if I had another set of equations like this, you know, like down here, x equals y equals and z equals.
Want me to do the other one too?
Please do. I'll do them all the way, or at least get them as far as you can without killing the plant. Then I could set this x equation to this x equation, and this y to this y, and this z to this z. We'll do that later, but okay. Last thought. We changed vector to parametric. Can you now change it to Cartesian? Hint, you don't want lambda in there anymore. Just x's and y's. Okay, let's see how you did. This one's going to go back to Henry.
I got y equals 1 plus x.
I'm going to ask you to tell me one thing at a time. What'd you get from this little equation? You learned something from that equation.
Lambda equals x plus 1.
You solve them all for lambda. Yep, lambda equals that. Lambda equals what here?
Y minus 2.
And the third one.
Z minus 3.
And since they're all equal to lambda, then you can put it in a big triple equation. That equals that, which also equals that. x minus 1 equals y minus 2, which equals z minus 3. And you can just leave it like that. That equals that equals that. You know, it's a little messy, but it's true. That's called changing to Cartesian. All right, could there be anything more? Yes, there can. So, this is where we're getting more complex, where we've got a ball that's kind of our vector. And it's at a certain place at a certain time. Everybody write this down. 4, 5, 6 is where it starts. I'm going to put an x, y, z in front. Plus t, now I'm doing t on purpose because it works well for time. Where is this ball at time equals 0? Where is that ball at time equals 1? And don't say 1, 2, 3, that's wrong. Where is the ball at time 0? Where is the ball at time 1? Pausing. All right, at time 0, it's super simple. You could put a 0 here, but it's just going to cancel out the whole second part. So it's just 4, 5, 6 is where he's at time 0. How about at time 1? Then you got to put a 1 here. And you would then say it's not at 4, 5, 6 anymore. It moves 1 in this direction, 2 in that direction, and 3 in that direction because we're only timesing by 1. That was actually pretty simple. So then that's 4 plus 1 is 5. 5 plus 2 is 7, and 6 plus 3 is 9. Raise your hand if you knew that. It was 5, 7, 9. Okay, awesome. Do you get if you did this on two different vectors, you could see if they were at the same place at the same time? Because at time 0, this guy's here. At time 1, he's there. What if you did this on another set of equations and you figured out that at time 1, the other vector was also at 5, 7, 9? Then you'd know they were in the same exact spot at the same exact time. All right, so that's the final types of questions is that. So here's one example of that. It starts at 2, 1, 3, and it goes lambda, don't want you to thinking it always has to be t, in 5, 1, 0. Okay, that's an equation. Here's another equation. I'll make it a different color. 12, 3, 3 plus t times 1, 1, negative 1. So the question is, do these vectors, which technically need an x, y, z in front, but it's kind of just wasting time, so, okay, fine, I'll put them. X, y, z, X, Y, Z, there. Okay. Do you think you could make a set of parametric equations for these two and then see if they are ever in the same spot as each other? I gave the example on my video the other day. When you guys walk out the door, do you get some of you are going to walk right through the middle of the door, and therefore you and the kid behind you will both be in the same spot, which is right in the middle of the door, but you'll be there at a different time, right? So the question is, could these guys have been in the same spot at the same time? If so, they collided with each other. That does happen. People run into each other, right? Okay, and could it also be that they were at the same spot, but at different times? All right, so you make your little set of equations here. X equals 2 plus 5 lambda. And it's just z equals 3. Well, that's kind of cool because 0 lambda is just 0, right? So sweet, I already know that z has to be 3, period, all the time. All right, for these little equations, I have x equals 12 plus t, y equals 3 plus t, and z equals 3 minus t. Could I say 3 plus negative t? Yeah, that would be the same thing. Then this and this get set equal. So that was a 12, wasn't it? Yep. Just drew over the 1. Okay, so now I have 2 plus 5 lambda equals 12 plus t. Highlight those to make it clear where they came from. That and that were equal, so that's where I wrote that. Next, everybody, do this and this. Set them equal in an equation. Isaac, what's the equation for the pink ones?
1 plus lambda equals 3 plus t.
Yep. Excuse me. I get this t equals 0, like t has to be 0 because of this last equation. Remember this was equal to that. And if I just solve that, doesn't t have to be 0? Huh? What does that mean? Time 0 is important. I know that much. Okay, now let's solve this one. And that can be solved using substitution. This is the one where kids that know their algebra are going to be fine, and why I've been banging on the drum of you need to know your algebra. So I'm going to solve this for lambda, and subtracting 1 from both sides, lambda will be 2 plus t, and then wherever I see a lambda in this equation, I can put a 2 plus t. So I go 2 plus 5 times 2 plus t equals 12 plus t. Five t equals t means that t must be 0 again. Okay, well, great. T is 0, server. So what am I supposed to do? At time 0 here, this one's at 12.33. Would this one, this equation here, have ever been at 12.33? Yeah. So how do you figure that out? You're right. At time 2. But how'd you figure that out?
Over my head, I just counted up, what's each of the, where it would be at lambda equals time 1, 2, 3, so on.
Okay. So at time 0, where is this guy? 2, 1, 3. Is that the same as 12.33? Of course not. At time 1, where is he? Well, you go 2 plus 1 times 5 would be 7. Is that right? No. But if you go to time 2, t equals 2. At time 2, piece it together for yourself that 2 plus 2 times 5 would be 10 plus 2 is 12. Oh my gosh, it's going to be at the same spot that the other one was at time 0, but it's going to be there at time 2. What does that mean? They were in the same spot, but not at the same time. All right. Would there have been a way to get that easier? These are not easy. Okay. But the fact that we knew exactly what time, we knew t had to be 0 from that one equation, that helped a lot. And I'd like to do one more because we're running out of time. And remember, we'll have time to practice this again tomorrow. So here is your last one. Ready? Last one for the day. 0, 1, 1 plus t times 4, negative 2, 2. I will tell you that this one will collide, as in it'll hit this red equation, but you have to tell me when they hit and where they hit. Systems of equations, what it's all about. I'll pause for a second while you write out this system of equations. And if you figure out that they hit at this spot, well, then you got one of the parts. But what time? This one might have been time 2, and this one might have been time 3. But if they are in the same spot at the exact same time, then they collide. All right, pause for a second. All right, that's all I got for you for today. These met at time 1, and they collided at 4, negative 1, 3.